We are going to introduce hardware implementation. Introduction, divisor. There are n-k plus 1 bits which either are predefined or all zeros. For example, choose 1011 or all zeros based on the leftmost bits of the augmented data bits. N-k bits are needed in XOR operation, 011 or all zeros. The leftmost bit is not needed because the result of the operation is always 0.
So as the following figure, we assume the augmented data bit is 10111010. In the operation, then we'll choose the divisor 1011. Because the leftmost bit of the augmented data bit is 1, then we skip the leftmost bit of the 4-bit 1011 divisor to 011. The reason we have talked before. However, in the figure, we got to notice D2 bit is always 0. The figure in your left hand is paper and pencil division process, and the figure in your right hand is hardware implementation process. The left one is shifting to the right 1 bit in each step, and the right one is shifting to the left 1 bit in each step.
Introduction, reminder. There are n-k bits. Use n-k register single-bit storage devices. In our example, n-k equal to 3, and we briefly mention the process. Assume the remainder is original or 0. Number 2. Repeat following action. Use the leftmost bit to make a decision about the divisor. The other 2 bits of the remainder and the next bit from augmented data are XORed to create the next remainder. So, you'll think, what does it mean, right? The simulation of the division encoder can help you to understand better. This is the simulation of the division encoder figure, and the single bit block is the register. As we've just mentioned, step 1, 2, 3 just left shifting 1 bit from augmented data word in order to push the first 3 bits to the remainder register. The situation just like there are 3 chairs in the classroom, and some students wait in line to see the chairs. Step 4, 5, 6, 7 can match the paper and pencil design. When we learn the leftmost bit is 1, we choose the divisor 011 and calculate as 1 XOR 1, and the result is 0, and put into the register. Follow the calculation rules, we can get the remainder successfully.
Simplify the design. The reason is that we don't need to keep the intermediate value of remainder bits. We only need the final bits. Only need 3 registers instead of 24 registers. And we don't need 21 XOR devices. 2 are enough, because the value of these columns are 0, so we skip the XOR devices. General design. We have n-k 1 bit shift registers in both the encoder and decoder. We have R2 n-k XOR devices, but the devices normally have several zeros in their pattern. Then different from the previous example, we use data word instead of augmented word.